the next hour-ish, we're gonna learn not everything, but how much ever I can teach you about AstroPi, which is a very important tool, especially if you decide to devote the rest of your life to astronomy, like some of us nerds do. So in today's lesson, I'll give you a quick, brief introduction on what AstroPi is, what are some sub-packages and associated packages you can use with it, and an insight into some of the most commonly used packages of AstroPi, and hopefully we can spare some time to answer all the questions you might have. And at least based on the groups that I talked to, I believe a couple of you are going to find this useful, given how astronomy related your projects are going to be. Surprise, surprise. Okay, so what is AstroPi? So as the name suggests, it is a Python package which offers a lot of tools and functions that you'll be requiring in different aspects of astronomy research, and not just, and when I say astronomy research, it covers the whole spiel, from planning and observation to reducing and analyzing the data from the said observation. And it also has a lot of other functions and tools to help you with numerical tasks like running numerical simulations, as well as for modeling based on data that you have. So to give you some idea about the sub-packages and how to use them, so AstroPi, unlike NumPy, for instance, you don't actually import the whole thing because AstroPi in itself is really big. So to be able to manage whatever sub-packages and libraries or little libraries of AstroPi that you are using for a script, this is the format you follow. From AstroPi, you will import whatever sub-package you want. But if the name of the sub-package is really clunky and hard to repeat over and over again, you can also do import astropi.subpackage as S, where S is an initial you can use, like you use NP for NumPy. Or within a subpackage, you can have multiple classes, and you realize that for your particular purpose, you just need one or two of those classes. So you can just import those classes alone, and so you'll have access to whatever functions are defined in that class. The AstroPi project community is fairly large, and it goes beyond just the AstroPi project itself, AstroPi and its sub-packages. You have coordinated packages, which are additional packages that need to be imported separately, but are maintained by AstroPi. And then there are what are called affiliated packages, which are other packages that are used for astronomy, but they are related to AstroPi, just not maintained by the people who maintain AstroPi. They give you they sort of expand on the functionalities and tools that AstroPi already give you. Here's a list of the 3 types of packages / utilities you can use. The names in bold are the ones that I'll be using in today's lesson. So you have these sub-packages that help you perform different types of calculations. One is called units that help you to convert between different units and perform arithmetic. I'll be showing an example of that soon. You have a sub-package that contains a number of physical constants that are very useful in astronomy, and it's very easily called constants. And there's a sub-package called coordinates, which contain classes and functionalities that help you extract celestial or spatial coordinates for different astronomical objects, whether they are different velocity or physical components and things like that. Some examples of coordinated packages are AstroQuery, which is very helpful when you have to look up information on a particular target. So instead of you having to look up the target on different websites like Simbat or Vizier, AstroQuery will let you put in the name of a source, and then it will do the online querying for you. Then there is CCD-proc, which does data reduction of images taken by a CCD detector. And then you have PhotoUtils, which is used for photometry. Photometry is basically about measuring the brightness of an object and doing some science with it. And PhotoUtils has plenty of tools to plot different kinds of apertures over different objects of choice over a CCD or any detector image, really, and be able to extract the brightness so you can do flux plots, find a signal to noise ratio, that kind of stuff. Then there are some affiliated packages which are not directly maintained by AstroPi, but are pretty much related and kind of expand on the tools AstroPi give you. So like AstroML, which I haven't used, but I've heard it's fairly useful for those interested in using machine learning in astronomy. Then there's Astro Plan, which I will show you an example of. It is to help you plan observations, as the name suggests. If you're interested in studying dust extinction, the interstellar medium, the dust extinction package might be useful. Now, to look at one set of sub-packages that AstroPy offers. And so before I go into the lesson, I would tell you to take a quick moment to go to the GitHub repo, and under day one on the README, there is a link to the collab, which has all the tasks that we have laid out for this session. And when you open it, you'll see some of the cells are already pre-filled because you'll be following through the slides, and some of them are going to be exercises you're going to be doing live. I uploaded the right thing? Yep, I totally uploaded the right thing. Yes.
It's just the AstroPy logo.
Yeah.
Okay.
And I'll upload the solutions app once I get back. So by tonight. Can I get a show of hands of how many of you have it open now? So. Okay, I'll give it a few more seconds.
Didn't quite catch the question.
So, sorry?
Didn't quite catch the question.
Oh, yeah, if you have the collab notebook opened, a show of hands so that I know how many people are, yeah. Okay, yes, I think we can go ahead. So the first sub-package I'll be talking about today is astropy.units. So you can import it like this, astropy.units is you, or you can import from astropy, import units as you. And the reason I use an initial is because anytime you're going to be using a units from here, you'll have to do units dot that unit, and writing 5 letters over and over again can be painful. So u dot is fine. And as the definition here tells you, it is very helpful when you're calculating and converting between different quantities. And especially when these different quantities have different units, it can be really helpful. Because otherwise you'll have to multiply it by factors of ranging from 100 to 10 raised to 20 or 30. Because like in astronomy, we have a general tendency of not sticking to one system of units. For distance alone, we can measure things from anywhere from kilometers, if you're describing things from ground to atmosphere, to parsecs. And if you have a calculation that involves different kinds of distances, in theory, they should all be in the same system of units, but instead of you having to multiply different factors, you're going to let astropy.units do that for you. So this is an example of how you would use it. Suppose I want to define a variable q, which is a velocity. I would multiply this velocity or the components of this velocity by its respective units. So I have a velocity that is 15.1 divided by 32 meters per second. So I would do it as 15.1 times u dot meter, or it can be u dot m, divided by 32 times u dot second, or u dot s. You always multiply the units because you can think of the units as being a factor of something, and it's the factor that you're multiplying with the quantity. So if you run your cell, you can see that I'm printing two things here, q dot value, q dot unit. Q is an object, and this object has many attributes. Value and unit are 2 of those attributes. So yes, if you run your cell real quick, you can see what the output should look like this. Value is 0.47, and the unit would give you the unit that it is in, meters per second. And this is a fun question. Does anyone know how to look up what attributes are available to any given object in your code? It can be an object that you created, it can be an object you imported from somewhere. Yeah.
So, right. So practice is.
Main, sorry?
So is it I help or so?
Not help. So, yes.
Do you just type your object and then the class and then add a question mark?
So the question mark sort of tells you what the object is. It doesn't tell you what sort of functions you can use with the object. But or I don't know if functions is the right word. What would you call attributes? Yeah. Attributes, yeah. So what attribute? So why don't you try typing dir and in parentheses q? That's a good question. So you get a list of things. So if you do q dot any of those, you will get the information that is attached with that attribute. So we use two over here, value and unit, but there's so many more. There's like things like item, there's like things like real, because some quantities can have a real part and an imaginary part. So for your complex numbers, for instance, and so it becomes very helpful if you do some insane calculations, some calculus involving these things, it can be useful. Now, this velocity right here is in meters per second. Distances also can be the distance is in meters, the time is in seconds. What if you want to convert between units? You have your object in one particular system of units, but your Astro reported in something else. You use the function or the attribute, no, the function dot to. So it's just like saying, take this object in this system of units and convert it to something else. So I have a distance here, which is 1 parsec. So 1 times u dot parsec or u dot pc would also work. So if I do x dot to u dot kilometer or u dot km, if you run that cell, you should get something like this. Or on Colab, if you print it, you'll have you won't have quantity, but you'll have everything else. Oh yeah, for reference, like whatever outputs I'm showing, these were run in my local terminals. On Google Colab, the formatting can be slightly different, but essentially will give you the same thing. Okay, everyone good so far? All right, so this was units. The other thing, which also sort of comes under the quantities functionality that AstroPi provides, is constants. Now, in astronomy, you would have noticed we love some constants named after people with some grand names and very grand values. You have your universal gravitational constant, the Stefan-Boltzmann constant. There is another Boltzmann constant, and many such constants. And instead of having to, define them as variables, attach them with their separate factors and figure out how to convert between units, AstroPi.constants already provides you those constants. It has pretty much all the constants you need for astronomical calculations. If there's something that's missing, you can always define a variable and attach the related units to it. So AstroPi.constants has these numbers and it takes the units from AstroPi.units so that you don't have to convert units yourself. So an example of this is is G, big G, which is universal gravitational constant. So if I import constants this way and print C dot G, you can run the cell and see that there is a certain set of information attached to that quantity. You have the value, you have the uncertainty. It will also tell you what the default units are in, which are typically SI units, and where it got that value from. So right now it's this value. If the value changes in 100 years, and assuming all of this still exists in 100 years, that reference will be updated as well.
That's a good question.
Yeah.
How can we get the list of the constants that are available within?
That is a good question. I know the read the docs for AstroPi constants has that list, but I haven't tried generating the list on my own here. Yeah, but if you go to the read the docs for AstroPi and then go to constants, it has the entire list. And they also have the option to request the maintainers to add a constant if it's really used and not there. Yeah.
Like dot to also work for units that are not like one unit, like for example, we used to like convert these to other units.
What do you mean by 1 unit?
Like for example, if you want to convert G into like some other units, it's not like SI unit.
Oh, yeah, it should work. Yes, as long as you define the units correctly, using the convention given by AstroPi.units, then yes. So this is the first exercise I have for you guys. Calculate the gravitational force between a 3 solar mass star and its 10 Jupiter mass planet. And the star and the planet are 2 AU away. These are the libraries that you can use. And I've given you some, the comments in the cell will have some helpful hints as to what units you may want to use. People on Zoom, how are we doing? I mean, I wouldn't see if you guys give a thumbs up, but I'm assuming you're doing great. All right, so this is what your answer should be. You can create these variables, M star, I call them M star and M planet, 3 solar masses and 10 Jupiter masses. You also have a unit called Earth mass because planetary scientists, we don't like to talk about things in kilograms because Jupiter and Earth are very heavy objects, so we would just like to use them as standard reference points for mass of a planet. And then AU is astronomical units, for those of you who don't know. And that's the formula, and you should get, this should be our answer, 1.89 times 10 to the 48. That's so those are the units that it has used because it assumes standard-ish units. Emphasis on ish because of AU square, but yeah.
Those units are kilograms, meters, AUs.
AU square, second square, because of, so the kilograms meter cube, second square, that should come from the masses and gravitational constant. The AU square is from the distance.
Yeah, but okay, because I'm like manually changing the star mass and planet mass and changing it to kilograms.
Right.
Yeah, it's happened for me too. It's giving me the results in Jupyter Math and so on.
Oh, I see. Okay, from Google Colab apparently does that. Okay, so if you're on Google Colab, okay, so this is new to me. But it should be correct. Yeah, it looks correct to
Do
me.
you want me to try this one?
Maybe, yes.
Yeah.
Yeah, so okay, so if for fun you try to convert both the star and planet masses to kilograms, you should get the answer that is displayed there. Okay, Google Colab is living in the future. I can't deal with this now. This will take me 2 naps to get over. Okay, everyone good? Let's move to the next activity in a bit. Okay, another set of things that we need to know is how to input files specific for astronomy, how to output said information. Now this is sort of general because there are different kinds of inputs and outputs that you'll be dealing with, depending on what kind of information you're processing or what you're trying to get out of the input information. But AstroPy sort of provides you this unified interface that helps you read data that's given in different formats and write it to a separate format that can be entirely different from the input. So one such example of that is table. So for example, let's say you have a .dat table of photometry information where someone has given you a table where they measure the brightness of many stars and saved it in ASCII format. Table will let you not only read this information but it will also let you write this information to a separate to a separate format. And this is especially useful if you're writing a paper, because most papers are written in LaTeX, either on a text editor or on something like Overleaf, which is also a text editor, but just a Google Docs version of it. And so instead of having to, type up everything by yourself using the LaTeX table subpackage, you can just have AstroPy.table do it for you. So you just need to copy paste the whole thing into your text editor or import it into your text editor, and it is not as painful. I couldn't find any good examples of data I could download and use, and hence that's why I don't have it in your notebook, but this is just an example for you to see. You can explore this further when you go to AstroPy.table. Read the docs is going to be your best friend. Now, another thing which I'm going to spend 2 or 3 slides talking about is something called FITS. FITS is very universal in astronomy. This is how astronomers save their data when they're observing with any possible telescope. In fact, it was a running joke when Biden sort of revealed the first JWST image to the world. People are like, how does he know how to open a FITS image? It's called Flexible Image Transport System, and it literally, the name is pretty much what it is. It is a very flexible way for anybody to open and access the contents of the image. Because if you think about it, you have all these observatories around the world, both on ground and in space, and they all run on different systems, different OSs, different people have created the instruments, different people operate it, different people wrote the software to run those. So what is something that can unify the language between those telescopes? And that is how those images are saved. And so they all use this format to save their raw data, because then it can be opened by people around the world, and you can read the raw data, you can process it the way you want, and then you can save it in whatever format you want. So FITS is something that we use to transport, analyze, and archive these scientific data. And it's also more useful than having to save your files as a .tiff or a .jpg or .png, because FITS can have multi-dimensional array of information. A lot of those arrays can be just the image and different components of the image, and it dedicates one dimension just to information about that image. So a FITS files it typically has multiple segments. The first main segment is called the primary HDU, or the primary array, and then you have something called image extensions. The HDU stands for header data units. I'll expand on that in a bit. And the primary array, or the primary header data unit, usually can either be a 1D spectrum, if you're just having one line of information. If you're doing spectroscopy, that's usually it. It can have a 2D image, or it can have a 3D data cube. A data cube is when you have multiple slices to your image. One layer can be the image, let's say in one wavelength. The next layer can be maybe the image in another wavelength, or it could be a spectrum of the object whose image you took. The third layer can be a kinematic map of that image. An easy example I can give you, which you can think about, is you've probably seen these JWST images of a single object in multiple wavelengths. That would be an example of a 3D data cube, because each slice would be a different wavelength. So a header unit is basically the information about that image. Or maybe actually no, labels for the information of that image. The labels are usually a sequence of 80 character keyword records. It is as simple as things like how big the image is, what are the dimensions of the image, how many rows or how many slices the image spans, to something more detailed. Who took this image? Which telescope took this image? What is the array and deck of the central target? Where was this image taken? When was this image taken? So you have the header unit, and then you have the data part of it, which is basically the information answering these labels of the details of the image. And this is especially useful because A, you need to know who to credit the image to when you're publishing it somewhere. B, for processing purposes, you would like to know where the target is so that you can look at it. You need to know when these things were taken, and it also gives you information that would be vital for reduction purposes, like how bright some target is, where are the darks and flats stored for all of these things. I'm not going to get into too much detail about it, because FITS images and how to process them is a separate lecture of its own. So here is another exercise for you guys. This should be, I'm not sure how well this is going to run on Google Colab, but let's see. So if you installed Anaconda, and that's how you're running Python, AstroPy also comes with the Conda installation. And with AstroPy, you also get some sample FITS files so that you can understand how FITS files work. And so for accessing the file path of the data that came with the AstroPy installation, we have this function fits.util.getTestData file path, which immediately prints out the file path for you. Otherwise, you have to go looking for it. So this is just for you to see what the header data unit looks like for a FITS image. So could you try running this cell and tell me if you get an output? If not, I can just show you what it is. Okay, so you do get an output on Google Colab. Okay, that's good. It should be there. Don't you go down? So keep going down. Oh, yeah, you open that.
Oh, okay.
Yeah. Okay. So it basically tells you what this FITS image contains. It has your primary header data unit, which is the first part of it, and then it has 3 dimensions of just the science data. So hdul.in. So if you open your FITS file like this, fits.open.info would give you the information about that file. Like that. It would give you what the type is, what the dimensions are, and what the format in which the data is saved. So what do you get from generating the data in the file? And what do you get? What do you think? Or yeah, another way of thinking about it is how do you think the values or the data in this file is stored, in what format? Maybe you want to guess first and then try. Do you think it's saved as a list? It's saved as a string? It's saved as a pandas table? What do you think?
A data frame?
Okay, that's one good guess, data frame, because that would seem very logical. Anybody else? Any guesses? Could be a NumPy array. I'm sorry? An AstroPy table, that is also very logical. So I have given you 2 ways in which, in your next cell, I've given you 2 ways in which you can get or output this data, either you can use fits.getData, and in parentheses, you would type in the file path, which you already have as fits image fn, or you can use HDOL1 because HDOL, remember, it's this big fat array with many elements to it, and the image is in 1, 2, or 3. So the first element of HDOL dot data should also give it to you. So fits.getData and then the file path, which is fits image fn, or you use only HDL. So there's two ways in which you can get the data. So what is it? What type is it? It's an array. It's an NumPy array. So it's very easy to handle. You can do basic calculations. You can plot it. So I haven't included this, but one thing you could try doing is just do import matplotlib.pyplot as plt and then do plt.imshow this data. And it should be, it's very uninteresting because this is a test file. Yeah, it's mostly dark, and then you have 3 differently colored pixels. Okay, that's just to show you how to extract data from a fits file. What you can do with this data, totally up to you. As I said, this is a NumPy array, so it's very easy to manipulate, remove elements, add elements, things like that. Yes. Now, how are we doing on time? We're doing on time, great. So I think this is a good point to sort of pause and take any questions, because the next part, it's the last part, but also the most detailed and involved part of this lesson. And I'm sure there you're going to have a lot of questions. So this is a good break to take a breather, or any questions you might have about what we've done so far. Yes.
When we call hdrel.info.
Yeah.
And we see the science images. Why is there 4 different rows for science images?
They're probably different. They're just different types of science images. Yeah.
What does the card column represent?
That is a good question, actually. I've never figured that out. I've always seen cards, but I've never really thought too much into it. Do you know?
No idea. Anybody else know?
Yeah.
Can look it up.
Oh, that will be great. Yes. Google is your best friend. Sorry?
So just so the Google Code app
Yeah.
doesn't have the Astro plan.
Oh,
so
yeah.
we need to install it manually.
Yes, that's a good point. I will add that note here.
Yes, I did. Yeah.
Good. Yeah. So I'm just gonna add this to the slides.
I think it's the number of header keywords
Oh, okay.
for.
That's okay. That those as cards, that would make sense.
That makes sense.
Yeah.
Yeah. Cool.
Okay, so if you have no questions, I'll just wait for them to get settled. Yes. Okay. So let's figure out how to plan observations, because that is a lot of work. So you have these packages, sub packages, and associated packages with AstroPy that help you plan observations. And when you're planning observations, you would need to think about, what target you want to look at, which days you want to look for that target, because because the Earth rotates and revolves around the sun, not all the stars are visible all times of the year. You want to think about where you're observing from. Are you observing from the northern or southern hemisphere, because you have access to different areas of the sky from both hemispheres? You want to think about what the moon cycle is, because if the moon is in front of the target, you obviously can't look at the target. And there are there are things like that to consider. And AstroPy stools really help you put those things into perspective and be able to plan those observations. Um, so here is something that you can start with. Let's say that I want to observe the star Fomalhaut from Subaru. And so first I need to generate the coordinates of the star and the coordinates of the observing site. So the packages that I've put down here are a hint. Astroplan does not come with Google Colab, so you want to pip install Astroplan first. You can just insert a new cell or in the same cell where you're importing Astroplan. Before you import it, you can just add this line, pip install Astroplan, and then you'll be able to install it. Okay, so this is how I did it, and there can be several possible solutions to this. So first, I use SkyCore to get the coordinates of Fomalhaut, which is just SkyCore dot from name Fomalhaut. What it does, it basically uses this name that you give it to conduct a query on different catalogs to get the coordinates for Fomalhaut. The default coordinates are going to be right ascension declination, which is basically the latitude and longitude of a star on the spherical in spherical coordinates. You can use AltAs if you want to convert those units to altitude and azimuth, which are a bit easier to visualize, but it is not mandatory for this exercise. It just makes it easier for you to understand. But we will be using AltAs shortly for the next part of the exercise. Now, to get the locations of Subaru, there are two ways you could do it. So getting the location means two things. You're trying to physically locate the latitude, longitude, and altitude of observatory. And you also need to figure out what time zone that observatory works in. Earth location is usually good about that. Astroplan, for some reason, it's not always good about it. So you have to specify what time zone it's in. US has many time zones. So US Hawaii is the time zone that Subaru works in. So you can use observer.at-site, or you can use what, sorry, how do you pronounce your name? Ocean, okay.
Yeah.
And yeah, so Ocean suggested the very easy way. It's Earth location dot offsite, you said?
Yes.
Okay, Earth location dot offsite, and then in brackets, you enter Subaru, and it will give you the information about Subaru's location. Then using the Earth location function, you define what are called the geodetic coordinates of Subaru. Geodetic coordinates are basically how far away from the center of the Earth is Subaru. So while we would refer to the location of something in latitude, longitude, and altitude, Earth location basically defines everything as a distance in meters from the very center of the Earth, because that's how AstroPy works. And it needs that information to do all the next calculations that you'll see some examples of. And so I was curious as to what units things are printed in, what things look like. And so I printed this statement. By default, it gives you the sky coordinates in RA and DEC. ICRS is the reference system that we use. Because the right ascension declination has to have a 0 point, and ICR is defined what that 0 point is, and the 0 point changes. And then the geocentric coordinates are all three of that. It's the X, Y, and Z distances in meters from the center of the Earth. Okay? Yes.
But here I'm confused because when we define from the Earth location, we didn't define like what is the height.
Oh, we don't have to, because it has the latitude and longitude of Subaru, and it's pretty smart enough to figure it out.
Okay.
Yeah, because using the latitude and longitude, it can tell it's something on Mauna Kea, and that is a known height.
Okay.
Yeah. But you can also define, there is lat long, and there is a keyword called height, which in most cases I haven't had to use, but you can use if you want. All right. So yes.
So this functionality retrieves data from syntax is here, right?
Yes. You're talking about SkyCore from name?
Yes.
Yes. You have SkyCore from name. You also have functionalities within the additional package Astro Query if you want to use that. Astro Query, although it's more than observation planning, it's used when you're looking and creating these tables of data. Yeah, because it has some fancy output features. Okay, so the next part of our task, I gave this as an optional exercise because I wasn't sure how much time we have. So it's no longer optional because we still have 9 minutes. So to be able to plot and visualize the observability of your target, because as I said, your target is not always up, you need to see when it's going to be up relative to when nighttime is at the observatory. You would need additional tools like astropy.time and astropy.visualization to plot and visualize where the target is going to be. So actually, can I? Okay, so I have filled out some parts of the subsequent cells for you to get started. Um, so before I go any further, I should take a look at what I have on the next slide without any spoilers. And let's see. Oh, so I don't have the next part on the slides, so I've got to switch here. So this is ultimately what we need as astronomers. We need to see when things are up and things are down, but I will show you how to get to that. Can people on Zoom still see my screen? Yeah.
Make it a little bigger.
Yes. So step 2 is to visualize and plot its visibility. So let's say that we want to observe the star on July 31st, 2024. So first, you need to define midnight. The reason midnight is usually a reference point because that's, 0 o'clock. 0 is a good, nice reference point that we can have right at the smack of the middle of a plot. And then we need to define a time range to calculate the position over. The time range we typically choose is 12 hours before midnight and 12 hours after midnight. So from noon of the previous day to noon of the next day, because then it is easier for us to figure out and plot where when sunset and sunrise are. You can also do from -6 to 6, but then sometimes the sun sets much up a little before 6 or sun rises much after 6, so you're not covering the full range there. And so that's delta midnight, and that plus midnight is going to be your time range. And for that, we use astropy.time. And then we obviously need numpy because we would need it for this np.linspace functionality, which you probably might have seen if you were in the numpy session. And u.hour is because time over here is typically defined in hours. So you need to make the units compatible to be able to do this addition right here. And then we set up a reference frame. And why do we need a reference frame? That you're going to see very soon. So we're setting up this reference frame in altitude and azimuth only because it's easy to visualize. Because if you notice, I have my final plot right here. I plot the altitude of the star at a given time because altitude is easy to see. Your horizon at 0, zenith at 90. So to get everything into that reference frame, we would use alt-as dot, where is it gone? Yeah, we use alt-as, we put in the observing times and location, and we set up this grid of values, which will be our reference frame on which we'll be plotting our transit curve. And then now we want to take this object and transform it to this frame. And because we've already created this object earlier, we can just use formalhow.transform to frame. Any questions in this cell? Clear? Okay. So now we want to figure out, even though we have this time range, where in this time range is it daylight versus nighttime? So for figure that out, you need to get the positions of the sun on that particular day. So for that, you can use astropy.coordinates. You can import get sun from astropy.coordinates. And then the next thing is up to you to figure out, for which I can give you 2 minutes. Your best friend generative AI should be able to help you. Even without generative AI, the first thing I would suggest is try to use the help functionality to see what getSun takes in as an import or how the class is structured. So then you'll know what you already defined and how you can use it with getSun to get the sun's position. Okay, did people get that done?
So like get some parentheses time
Ye-
and then transfer to the friend.
Yes, exactly. So get sun, you put in the time, so you define the time range within which you need, so if you, let's see. So get sun times, and then if I do sun alt as, so that I can put the sun on the reference frame, just like we did with formal out. I would do sun, sorry, sun times dot transfer to. Oh, come on. I did it, okay? It's right there. Or you can, yeah, do all of that in one single line. All right, so now we have the sun. Technically, we would need the moon's position as well, but let's assume it's a new moon night. And now we want to plot it. So you can use whatever time is left until 5 o'clock to fill in this. And please ignore the spelling mistakes.
I have a question.
Yes.
So if like the astral plane can automatically determine whether it is a new moon or.
Yeah.
Okay.
Yeah, so just like get sun, you have a similar thing for the moon. I don't remember off the top of my head, but you can similarly you can use a similar thing to predict what the moon phase is going to be that night.
Okay.
And to like track the motion of the moon. Because you can still observe if it's a full moon night, you just cannot observe when the moon is in your way. Unless, of course, you're using a radio telescope, then you don't care. Okay, it's 5 o'clock, so you guys want 30 more seconds or should we move on? Okay, let's see. Has someone figured out how you can plot the sun's altitude? So, okay, I should have made the comment clearer. You're plotting the altitude against the time because you need to see where the sun is going from, well, from at least twilight to sunrise, because that's when you're observing, or that's when you can possibly observe. So now that you know that, how would you plot the sun's altitude? So using alt as, you can extract the altitude and azimuth separately, which I have done partially over here. This, or sun alt as dot alt. That would be our y-axis, or the y data, and the x data would simply be the values of in the time frame that you've defined right here. Okay, and then you would do the similar thing for Fomalhaut. I personally used a color map to represent azimuth. I sometimes do that. And I also thought it might be a good idea because for some people it might be useful. And depending on how much your dome can turn, because a lot of observatories are on alt-as mounts. That is a separate conversation we can have if you're interested. It is a useful piece of information to know. So this is what you would do. You would plot delta midnight, which is your time range, the np.linspace array, against the altitude of the sun. And then, yes, you can give it a different color, label it sun because you have multiple lines, so always good to have a legend. And then I would use a scatter plot because it is many different individual values, and plot same X data and take the altitude of Fomalhaut now. And then it is if you're someone who cares about when daytime is nighttime is, basically if you're observing using a regular telescope and not a radio telescope, you need to know when you can observe. So it is useful to highlight the period between sunrise and sunset and the period of total darkness that comes in between. So this is sort of the range we use. The range of twilight is when the sun is between the horizon to, I would say, a little below, little less than 20 degrees below the horizon, because that's when the sky is orangey and beginning to get dark, and nighttime is when the sun is below 20 degrees below horizon. So we use that information, and then you can use plot a plt.fill between, which will fill a patch of color between an X range or between a Y range, depending on how you define it here. And then I just add some additional details. I limit X from -12 to 12. You can limit it further, or I limit the Y limit, that is the altitude, from 20 to 90, because using Wanakee observatories, you can only observe above, 20 is way too low. You have to observe from around 24-ish to zenith and back the other way. And I have to tell you, I forgot to mention, the times here are in UTC, Universal Time Coordinates, so which is why it does not look dark in the middle as you would expect it, but you can always convert time to local time, which in this case would be Hawaii Standard Time. So this is what your plot would ultimately look like. And as you can see, the highest that Fomalhaut gets to is 40 degree, which is not ideal because then when you're slanting your telescope, you're looking through a lot of atmosphere. So the best observing condition would be at zenith if the star is directly overhead, or maybe if it's like kind of at, I'd say 60 to 70 degrees. But this is the observability. And so if I was a telescope operator, I would say you can observe, you can observe Fomalhaut maybe like around this time range and this time range, because I would be hesitant to waste precious telescope time going to that low of an air mass. But sometimes people look at targets that don't rise up as much because of where they're located in the sky. So you have to take the best of the circumstances. So this is a very easy, neat way to plan observations. I will be uploading this answer key shortly. I can also upload an alt-as notebook, which is far less commented and way dirtier than I use, so that you can see how things happen. Because like when we plan observations, we're not planning just for one target. We're planning for multiple targets. So because I have to observe next week, I'll be working in that notebook sometime today or tomorrow. So I will upload that as well to give you an idea of how you can. And so that involves pretty much all the libraries you learned about today. It has NumPy, it has got pandas, it's got matplotlib, it's got this. And yeah, if you have any questions, yes, you can ask me now.
So I was wondering if there is like a function available that we can automatically determine, so which is the best time to observe a target with the best observing condition.
So observing conditions is multifaceted because it's not just dependent on time, it's also dependent on weather.
Yes.
I am pretty sure there are packages that let you make weather maps, but as far as I know, they're not built into AstroPi.
Yeah,
So,
but I mean.
oh, but if, like,
how
so,
to- Yeah,
so basically generate this plot, but not having to go through all these steps?
no, so what I actually mean is like, so to ensure that the operate is, so it just like when we write the proposal, so we propose the time of the observation.
Yes.
So we do not know the weather, but we know like what is the expected.
Oh, I see what you mean.
Yeah.
As far as I know, I don't know of any such package or sub-package within AstroPi.
Yeah.
I have to go through the same process, generate these plots, so I know what targets to propose for.
Yeah.
But that could be a group's project, if you'd like to create a library for that.
Sure.
Yeah.
Yeah, I can show
And
you.
these are some references I used, if you want, you can, these, yeah, but docs.astropy.org basically has all the information you need.
Yay.